This is again showing the mole fractions over here. How mole fraction is CO is 2000 ppm of CO is considered a flame, and you can see over here, the flames are almost touching the tube, high temperature. Whereas when we put the inclined firing, we are able to get flames more towards the wall, and this is all clear. And you can see almost 90-degree reduction in the tube metal temperature. So I think it has a place. If you are having any issues on high tube metal temperatures, you can talk to us and we will be able to see whether your furnace is a good candidate for inclined firing, whether it can, really reduce the tube metal temperatures. All right, that's all I had. Here is an open question. What is the maximum tube metal temperature of ethylene cracking heaters? You can type your answer. Okay, show answers. Let's see. I think these could be centigrade actually. That's what I'm kind of thinking. 15 to 1600 degree looks low, but 2000 degrees, 1950, they look right. Well, thank you for participating and providing these numbers. We have another quiz coming up, multiple select. What are the key elements in selection of right metallurgy for cracking furnaces? Okay, this should be pretty simple. Well, most of you got it right, all of above, Cost, run length, tube metal temperature. Thank you. Give me a feedback if you like these quizzes. We want to see, whether this effort is worth it, or we can go back to our normal PowerPoint presentation. Your feedback is important because this webinar is for you. So we just want to get your feedback if you have any suggestions. Metallurgy selection, coil metallurgy. Nowadays, we are going anywhere between 35 nickel, 25 chrome. The factors which affect the coil material are operating temperature, tube service life, cost, carburization resistance, creep rupture strength. So all these factors basically affect the coil metallurgy, what you select. But I think the good news is we have coils which can go up to, this is 1830, but we can go even higher. And as I said, localized overheating must be avoided, and that's where the flames can help you out. Improving the flame patterns will really help you out. Radiant coil generally in other heaters is only 10 to 15%. Here it is 33% of the furnace capital cost. And it only lasts 5 to 7 years, does not. Generally we talk about 100,000 hours, which is about 12 years for most of the other furnaces, but here we're talking of only 5 to 7 hours. And the reason is because of carburization, the tubes can, give way and we have to change the tubes. Well, these are some of the metallurgies which are used. HK40 has been there for ages, almost 30 years, or maybe more, I should say 50 years. HP low carbon, from HK40 when we get to HP, we increased it by 100 degrees. Then we went to HP microalloys, we increased it by another 100 degrees. Then we went to HP modified, which is pretty the same, and then 35 chrome, 45 nickel, we can go up to about 2100 degrees. And this may not be the end, actually. You may still be getting more. I don't know whether our metallurgist can come up with an alloy, and that's really good, actually. It has been a big improvement, the coil metallurgy. And besides this, there are a lot of other things. The vendors are coming out. They are coming out with mud. They are coming out with coatings. They say if you have aluminum coating, it kind of repels carbon, so you can, do that also. So there are lots of technical things which are taking place. Next, we want to talk about transfer line exchangers. They are important because you want to cool the product from the heater very, very quickly so that you don't have any undesired reductions. So that is done in transfer line exchangers in very, very quickly. And as you can see here also, the residence time is very, very fast, that in you cool it down, very, very fast. In five milliseconds, you cool it down. So you can avoid, Well, let's move on to convection section. As we have said, radiant efficiency is only around 40-45%, out of which 30% is used in the reaction and 12% is used in the approximately in the process preheating. And then these flue gases leave the radiant section, enters into convection section. And in convection section, we are talking of preheating the process, and which again is about 35%. And then 16% is used in high pressure steam generation, high pressure steam superheater. So that's, and then the stack losses are only about 5%. That's what we are kind of, Convection sections have typically been the same no matter whose furnace you are going. You will always have a horizontal box. It will be slightly offset. That's generally the design, and these are the different services we have in the convection sections. This is showing a crossover, from the radiant section to convection section. And a lot of times this area generates or radiates so much heat that you can even start getting coking or tube overheating in this bottom area because of the lot of high temperature flue gas volume. So it kind of accumulates the radiation and starts going into the shield tube. So you need to kind of calculate and make sure. Also, even though we are showing it like this, in reality, it may not be that uniform, depending on the design. So that also needs to be taken into consideration. So what are we trying to do in convection section? We are trying to recover the heat, and that is for minimizing energy cost. So we want to recover the heat, and that heat is used for preheating the liquid feedstock, or if you have a gaseous feedstock, then we preheat the gas feedstock. For preheat boiler feed waters, generate superheat steam. Then also we preheat dilution steam, and then preheat the dilution steam plus hydrocarbon mixture. That's typically what we do in the convection section. Convection section generally will have two sections. We'll have a shield or shock section, and the second one will be extended surface sections, which are fins or studs. And the basic equation, just like any heat exchanger, is UA LMTD. So convection section design is much simpler. It's almost like a fin fan cooler, And I'm just giving you an equation which is for calculating heat transfer coefficient. And as you will see, there are two parameters I want to talk about. One is the flue gas mass velocity, and the other is the tube OD. And you will see the higher the velocity, the higher the mass velocity, the more heat you will get transferred. And the second is the tube diameter. The lower the tube diameter, better heat transfer you will have. So if you can use 3-inch tubes as compared to 4-inch tubes or 6-inch tubes, you will get better heat transfer. And one thing which I forgot but might have told you is whether it is the radiation section or the convection section, all the heat transfer in these furnaces is controlled by the flue gas. Whether it is a radiation, convection, the heat transfer is controlled by the flue gas. So even though we call it a convection section, but the flue gas temperatures are very, very high. So we have a substantial amount of radiation taking place in these furnaces. The radiation is because of the presence of hot flue gases. It's also because of the presence of hot flue gases between the tubes and then from the convection walls. And I told you about the mass of the hot flue gas before in the crossover. And generally, they will use bare tubes unless the flue gas is cooled down to about 14 to 1600 degrees. That's generally the design, this thing. So the question is, why use fins? Why do we use fins? So as I just a moment ago said, the heat transfer is controlled by the flue gas. So if you're talking of any fluid, the inside heat transfer coefficient could be anywhere between 100 to 200 or even 300. And the outside heat transfer coefficient is generally of the order of between 5 to 8 or 5 to 10. So as a result, it's the outside heat transfer coefficient which is controlling the heat transfer. Or anytime that happens, we can provide more surface on the outside and control or improve the heat transfer. And that is the one biggest change which has taken place in the last 50 or 60 years is use of finned heat transfer. When we fin the tubes, we are able to increase the outside surface area almost 10 to 12 times. And by doing so, we are able to replace 3 bare tubes or even 4 bare tubes with one tube, one fin tube. That is how effective finning is. And as a result, the convection sections have become very compact. They have become much economical because they can be fabricated in shops and then they can be shipped in modules. So finning really, really helps in heat transfer. And that is because the heat transfer is controlled by the flue gas side. So this is sketches showing you the different components of a convection section. We normally have casing on the outside, and we have intermediate tube sheets. You can see over here, 2 end tube sheets by which the tubes are supported. Then we have these header boxes where the return bends are housed. We have refractory lining on all the sides for insulating the casing. And That's basically it, the convection section, you know. This is showing you the intermediate tube sheets. The horizontal tubes require tube supports every 35 diameters. And because of that, you put these intermediate tube sheets. These are of high chrome nickel because they are experiencing high tube metal temperatures or high, yeah. And then you can see the header boxes, you can see the inlets, you know, you can see the return bands. This bottom are bare tubes, and you can see the fin tubes and the provision for future rows. So those are all these common things, you know. So some of the things which is available is, I mean, the feed is available at low temperatures, you know. Actually, the feed, if it's a gas feed, it's available at as low as 150, you know. So we preheat it and then we mix it with steam and heat it all the way up to 1100 or 1200. And the flue gas from the radiation section is almost is as hot as 1100 to 1150 degrees centigrade. And we can cool the flue gases to anywhere around 110 to 150 degrees centigrade. Approach between flue gas and fluid can be done like 15 degrees centigrade or 25 degree F. What we are preheating is feed preheat, combustion air preheat, or boiler feed water preheat. Those are the things we are preheating in the cold end. But you can see how monstrous the convection section is, actually, how big the convection section is. This shows you the flue gas temperature profile and the fluid temperature profile. This is where the flue gases are entering the convection section at about 2100 degree F. And then slowly we are cooling it down all the way to 253. And we have first one is lower mix preheat. Then we have dilution steam superheater. We have a lower HP steam superheater. Again, another middle HP steam superheater. Then we have a mixed feed preheat. Then again, HP steam superheater. You can see that. And then finally, the boiler feed water preheat and mixed preheat, you know, over here. So we have been able to extract the last. You know, you can see it's only about 70 degree. And most of the heating is co-current, except these two, which are counter current. But most of the heating is co-current, and you can see over here. This is a coil arrangement, a typical coil arrangement because of gas preheating. Yeah, I still have a few minutes. So this is for the gas feedstock, a typical this thing. This is for a liquid. The only difference is you vaporize the liquid, so you had to give another this thing. And we said just like that, this is the flue gas temperature profile for the same heater. What are the issues in convection section? Some of the issues are non-uniform flue gas distribution, even though it's not very common. Convection section fouling is pretty common, and lower crossover temperature is even more common. I mean, a lot of times those convection coils don't behave as they should have, and that could be a shortcoming in the design. And as a result, the crossover temperature is not what they were supposed to be designed, so you end up firing it harder, actually. So we still have a few minutes left. Let's talk about the furnace draft. There are two types of draft we utilize in these furnaces: natural draft and induced draft. And in the old days, the convection sections used to be small, and we would design them with lower flue gas mass velocity, so we could have natural draft furnaces. but not anymore. I mean, now we have large convection sections, and the convection sections can have anywhere between 30 to 50 tube rows. That's how deep the convection sections are built. The pressure drop across the convection sections could be anywhere between 3 to 5 inches of water column. And if you have an SCR, then you can add another 1 or 2 inches or 3 inches of pressure drop. So there is no way the stack can provide that type of draft. So you end up using an ID fan, induced draft fan. This is another one installation, and this is another installation with 2 fans, So that's what you end up using it. One thing we want to talk about is draft control, because everybody talks of O2 control, and that is only half the story. When you talk about O2 control, I mean, everybody, all the people who are in operations, they talk about what O2 you are maintaining, but nobody talks of the draft, because draft is equally important as excess O2. Anytime you make a change, you are make a change to one parameter, the second parameter automatically gets affected. The good news is that the oxygen analyzers have improved substantially. There is a big improvement in oxygen analyzers, so we have very reliable oxygen analyzers. The heaters are not pressure-tight structures. Air can leak from different openings, if there are any openings, peep doors, expansion joints, penetration seals. And this O2, which is leaking, is called trampair. It does not take part in combustion. It shows up in the oxygen analyzers, and it kind of messes your O2 control. So our effort should be all the O2 which is going into the furnace should be coming from this thing. And this kind of shows you a draft profile. You can see how much. This is at the burners, this is at the arch, all negative, and then these are all the pressure drop in the convection section. And then we have an ID fan which provides a required draft, and then it sends it to the stack. This is a simple guideline based on ID fan damper and burner register. If your O2 is high and draft is high, close the ID fan damper. Or if your O2 is high, draft is low, close the burner register. So it's a very simple guideline for you. So thank you very much for giving me a patient hearing. We just want a little bit of feedback from you. If you can give it to us. Did this webinar meet your goals? Well, thank you. Was the course content clear and easy to understand? Thank you. And I think the last one is over here. Thank you. I think I need improvement, honestly. I'm trying, actually. I was trying to rehearse on PowerPoint, and it gave me a very good feedback. It said you need a lot of improvement. Well, thank you very much. We hope we will be able to see you again. Let's see if there are any questions here. Oh, I hope all of you were able to hear me because one of them is saying the volume stopped working. So if that was the case, I really apologize. So thank you all.